Hi! Welcome to the fifth module of the Python Fundamentals course, where we look in more depth at the built-in collection types of the Python language and explore the various protocols that unite them. In this module, we'll revisit some collection types we've already explored. Str, or string, the immutable sequence of Unicode code points. List, the mutable sequence of objects. And dict, the mutable mapping from immutable keys to mutable objects. We'll also cover some new ones. Tuple, the immutable sequence of objects. Range, for arithmetic progressions of integers. And set, a mutable collection of unique immutable objects. We won't cover the bytes type further here. We've already discussed its essential differences with str, and most of what we learn about str can also be applied to bytes. This is not an exhaustive list of Python collection types, but it's completely sufficient for the overwhelming majority of Python 3 programs you'll encounter in the wild or are likely to write yourself. In this module, we'll be covering these collections in this order, and then round off with an overview of the protocols that unite these collections, which allow them to be used in consistent and predictable ways. First up is tuple. Tuples in Python are immutable sequences of arbitrary objects. Once created, the objects within them cannot be replaced or removed, and new elements cannot be added. Tuples have a similar literal syntax to lists, except that they are delimited by parentheses rather than square brackets. Here's a literal tuple containing a string, a float, and an integer. We can access the elements of a tuple by a zero-based index using square brackets. And we can determine the number of elements in the tuple using the built-in len function. We can iterate over tuples using the for loop, and we can concatenate tuples using the plus operator. Tuples can be repeated using the multiplication operator. Since tuples can contain any object, it's perfectly possible to have nested tuples. We use repeated application of the indexing operator to get to the inner elements. Sometimes a single element tuple is required. To write this, we can't just use a simple number in parentheses. This is because Python parses that as an integer enclosed in the precedence controlling parentheses of a math expression. To create a single element tuple, we make use of the trailing comma separator, which we're allowed to use when specifying literal tuples, lists, and dictionaries. A single element with a trailing comma is passed as a single element tuple. This leaves us with the problem of how to specify an empty tuple. In actuality, the answer is simple. We just use empty parentheses. In many cases, the parentheses of literal tuples may be omitted. This feature is often used when returning multiple values from a function. Here we make a function to return the minimum and maximum values of a series, the hard work being done by the two built-in functions min and max. Returning multiple values as a tuple is often used in conjunction with a wonderful feature of Python called tuple unpacking. Tuple unpacking is a destructuring operation which allows us to unpack data structures into named references. For example, we can assign the result of our min-max function to two new references like this. Tuple unpacking works with arbitrarily nested tuples, although not with other data structures. This in turn leads to the beautiful Python idiom for swapping two or more variables. Should you need to create a tuple from an existing collection object, such as a list, you can use the tuple constructor, here also shown for strings. Finally, as with most collection types in Python, we can test for containment using the in operator, or non-membership with the not in operator. While that just about wraps up our look at tuple, let's move on to the next collection type. We've covered strings at some length already, but we'll take time now to explore their capabilities in a little more depth. Recall that str is a homogeneous, immutable sequence of Unicode code points, which for the most part we can consider to be the same as characters. Let's put str through its paces. As with any other Python sequence, we can determine the length of a string with the built-in len function. For instance, If we wanted to know how many characters were in the Welsh place name Llanfair Pwllgwyngyll Goga Uchaldopos Llantysilio Gogogok, we could call len on this string and get the answer 58. Concatenation of strings is supported using the plus operator. For instance, it's easy to turn new found land into Newfoundland. Although for joining large numbers of strings, the join method should be preferred because it's substantially more efficient. This is because concatenation using the addition operator or its augmented assignment version can lead to the generation of large numbers of temporaries, with consequent costs for memory allocation and copies. Let's see how join is used. Join is a method on Str which takes a collection of strings as an argument and produces a new string by inserting a separator between each of them. An interesting aspect of join is how the separator is specified. It is the string on which join is called. As with many parts of Python, an example is the best explanation. To join a list of HTML color code strings into a semicolon separated string, we call join on the separator we wish to use, the semicolon, and pass in the list of strings to be joined. We can then split them up again using the split method, which we've already encountered, but this time we're going to provide its optional argument. A widespread and fast Python idiom for concatenating together a collection of strings is to join using the empty string as the separator. The way may not be obvious at first. To concatenate, invoke join on empty text. Something for nothing. This use of join is often confusing to the uninitiated, but with use, the approach taken by Python will be appreciated as natural and elegant. Another very useful string method is partition, which divides a string into three sections: the part before the separator itself, and the part after the separator. Partition returns a tuple, so this is commonly used in conjunction with tuple unpacking. Here we separate the string London:Edinburgh into three by partitioning around the colon. Often we're not interested in capturing the separator value, so you might see the underscore variable name used. This is not treated in a special way by the Python language, but there's an unwritten convention that the underscore variable is for unused or dummy values. This convention is supported by many Python-aware development tools, which will suppress unused variable warnings for underscore. One of the most interesting and frequently used string methods is format. This supersedes, although does not replace, the string interpolation technique used in older versions of Python, and which we do not teach here. The format method can be usefully called on any string containing so-called replacement fields, which are surrounded by curly braces. The objects provided as arguments to format are converted to strings and used to populate these fields. The field names, in this case 0 and 1, are matched up with the positional arguments to format, and each argument is converted to a string. A field name may be used more than once, such as in this example. However, if the field names are used exactly once and in the same order as the arguments, they can be omitted. If keyword arguments are supplied to format, then named fields can be used instead of indexes. Note in this example how we've used the ability to split long statements over multiple lines so long as the split is inside open parentheses, brackets, or braces. In this case, we split the argument list to the format method inside its open parentheses. This technique can greatly aid the formatting of Python code whilst keeping a manageable line length. It's possible to index into sequences using square brackets inside the replacement field. Here we've assigned a tuple to a variable pos, and then we pass pos as a keyword argument to format. We access the elements of pos inside the replacement fields within the string. We can even access object attributes. Here we pass the whole math module to format using a keyword argument. Remember, modules are objects too. Then we access two of its attributes from within the replacement fields, pi and e. Format strings also give us a lot of control over field alignment and floating point formatting. Here's the same with the constants displayed to only 3 decimal places. We don't cover all of the intricacies of the Python formatting mini-language. If you want to know more, consult the documentation. Now we've covered the fundamentals of the string type, we recommend you spend some time familiarizing yourself with the other string methods. Remember, you can find out what they are using simply help str. Let's move on now and look at the next collection type. Let's move on and look at range, which really is a collection rather than a container. A range is a type of sequence used for representing an arithmetic progression of integers. Ranges are created by calls to the range constructor, and there is no literal form. Most typically, we supply only the stop value. In this case, we create a range from 0 to 5 simply by supplying the stop value of 5. Ranges are sometimes used to create consecutive integers for use as loop counters. Note that the stop value supplied to range is one past the end of the sequence, which is why the previous loop terminated at 4 and didn't print 5. We can also supply a starting value if we wish, such as in this call range 5, 10. Wrapping this in a call to the list constructor is a handy way to force production of each item. The so-called half-open range convention, with the stop value not being included in the sequence, at first seems strange, but actually makes a lot of sense if you're dealing with consecutive ranges, because the end specified by one range is the start of the next range. Range also supports a step argument, which controls the interval between successive numbers. Note that in order to use the step argument, we must supply all three arguments. Range is curious in that it determines what its arguments mean by counting them. Providing only one argument means it is the stop value. Two arguments are start and stop, and three arguments are start, stop, and step. Python's range works this way so the first argument, start, can be made optional, something which isn't normally possible. Furthermore, range doesn't support keyword arguments. You might almost describe it as unPythonic. At this point, we're going to show you another example of poorly styled Python code, one you can and should avoid. Here's a poor way to print the elements in a list using range, len, and list indexing. Although this works, it's most definitely unPythonic. Always prefer to use iteration over objects themselves. If for some reason you need a counter, you should use the built-in enumerate function, which returns an iterable series of pairs, each pair being a tuple. The first element of the pair is the index of the current item, and the second element of the pair is the item itself. We can improve this even further by using tuple unpacking and avoiding having to deal directly with the tuple. Because of the strong iteration primitives built into Python, ranges aren't widely used in modern Python code. Let's move on and look at the next collection type. We've already covered lists a little, and we've been making good use of them. We know how to create lists using the literal syntax, add to them using the append method, and get at and modify their contents using the square brackets indexing. Now let's take a deeper look. Let's start by making a list containing the words show how to index into sequences. We'll do this by calling the split method on a string. We're already familiar with how 0 and positive integers index the list from the front using a 0-based index. Here we extract the fifth element by using the index 4. One very convenient feature of lists and other Python sequences, for this applies to tuples too, is the ability to index from the end rather than from the beginning. This is achieved by supplying negative indexes. For example, we can access the fifth element from the end by supplying the index -5. The last element of the sequence is at index -1. Negative indexing is much more elegant than the clunky alternative of computing the forward index by subtracting the backward index from the length of the sequence. Note that indexing with -0 is the same as indexing with 0, returning the first element in the list. Because there is no distinction between 0 and -0, negative indexing is essentially 1-based rather than 0-based. This is good to keep in mind if you are calculating indexes with even moderately complex logic. Off by 1 errors can creep into negative indexing fairly easily. Slicing is a form of extended indexing which allows us to refer to portions of a list. To use it, we pass the start and stop indices of a half-open range separated by a colon as the square brackets index argument. Here we slice three words from the list by passing the start index 1 and the stop index 4. This facility can be combined with negative indexing. For example, to take all the elements except the first and last, slice between 1 and -1. Both the start and stop indices are optional. To slice all elements from the third to the end of the list, supply only 3 colon as the argument to the index operator. And to slice all elements from the beginning of the list up to but not including the third, supply colon 3 as the argument to the index operator. Notice that these two lists together form the whole list, demonstrating the convenience of the half-open range convention. Since both start and stop indices are optional, it's entirely possible to omit both and retrieve all of the elements, and indeed this last example is an important idiom for copying a list. This new list has a distinct identity, but an equivalent value. It's important to understand that although we have a new list object which can be independently modified, the elements within it are references to the same objects referred to by the original list. In the event that these objects are both mutable and modified, as opposed to replaced, the change will be seen in both lists. We teach this full slice list copying idiom because you are likely to see it in the wild and it's not immediately obvious what it does. You should be aware that there are other more readable ways of copying a list, such as the copy method, or even a simple call to the list constructor passing the list to be copied. Largely, it's a matter of taste. Our preference is for the third form using the list constructor since it has the advantage of working with any iterable series as the source and not just lists. You must be aware, however, that all of these techniques perform a shallow copy. That is, they create a new list containing the same object references as the source list, but don't copy the referred to objects. To demonstrate this, we'll use nested lists, with the inner list serving as mutable objects. Here's a list containing 2 elements, each of which is itself a list. Let's look at what's going on under the covers as Python constructs this data structure. First, 2 integer objects are created containing the values 1 and 2 respectively. The elements of the first inner list are references to these 2 integer objects. Now 2 more integer objects are created containing the values 3 and 4 respectively. The elements of the second inner list are references to these integer objects. Now the outer list is created, its elements containing references to the 2 inner lists. Finally, the reference named A is bound to the outer list. What happens when we copy the list? Here we use the full slice technique, but any of the 3 techniques we've shown will have the same effect. We're requesting a copy of the outer list, so its elements, which contain references to the 2 inner lists, are duplicated. These references refer to the same inner lists as the original list A. Once the list copy is complete, we bind a new reference named B to the new list. We can confirm that the lists are distinct objects by testing with A is B, which returns false. They do, however, contain equivalent values, which we can test with A equals B, which returns true. Not only are the elements at A0 and B0 equivalent, they actually refer to the same inner list object. Now let's replace the element at A0 with a new list containing 8 and 9. This results in the construction of 2 new integer objects containing 8 and 9 respectively, and a new list, the elements of which are references to these 2 new integer objects. The reference in A0 is redirected to point to this new inner list object. And we can confirm that A0 now indeed points to the new list, whilst B0 is unmodified. What happens if we now append to the inner list referred to by A1? Let's append a new integer object containing the value 5. The new integer object is created and is referred to by an additional element in the inner list referred to by A1. So A1 now refers to a list containing integers 3, 4, 5. Significantly, because A1 and B1 refer to the same inner list, the list accessible through B1 has also been modified. Following these manipulations, the data structure referred to by A is a list containing two elements, each of which is itself a list. The first inner list contains 8 and 9, and the second inner list contains 3, 4, and 5. The data structure referred to by B is also a list containing two inner lists. The first element refers to a list containing 1 and 2, and the second element also refers to the 3, 4, 5 list. As for strings and tuples, lists support repetition using the multiplication operator. It's simple enough to use. Here we repeat a list containing the integers 21 and 37 4 times. This form is rarely spotted in the wild. It's most often useful for initializing a list of size known in advance to a constant value such as 0. Here we create a list initialized with 9 0 elements. Be aware though that in the case of mutable elements, the same trap for the unwary that occurred with list copying lurks here, since repetition will repeat the reference without copying the value. Let's demonstrate using nested lists as our mutable elements again. We'll repeat a list 5 times. The mutable element it contains will be another list containing two elements -1 and +1. Let's see what Python needs to do to construct this data structure. First, two integer objects are created containing the values -1 and +1 respectively. These are referred to by the two elements of the inner list. Python then creates the outer list and arranges for its single element to contain a reference to the inner list. Now the repetition operation is applied. A new list is created containing 5 elements, each of which contains a copy of the single element in the original outer list. All of these elements contain references to the same inner list object. Now the temporary single element outer list can be disposed of. Finally, this whole data structure is bound to a new named reference S. As expected, S contains 5 elements, each of which is the -1 +1 inner list. Now let's append the integer 7 to the fourth inner list at index 3 on the outer list. This creates a new integer object and a new element on the inner list containing a reference to that integer object. We can see that all of the elements of the outer list have been modified because they do in fact all refer to the same inner list. To find an element in a list, use the index method passing the object you're searching for. The elements are compared for equivalence or value equality until the one you're looking for is found and its index returned. Here we create a list W containing the words "the quick brown fox jumps over the lazy dog" using the string split method. Searching for fox using the index method returns the integer 3, which of course allows us to get hold of that element. If you search for a value that isn't present, like unicorn, you'll receive a value error, which we'll learn how to handle gracefully in the next module. Another means of searching is to count matching elements using the count method. Here we count occurrences of the word "the." If you just want to test for membership, you can use the in operator, or for non-membership using the not in operator. Elements are removed from lists using a keyword with which we have not yet become acquainted, del. The del keyword takes a single parameter, which is a reference to a list element, and removes it from the list, shortening the list in the process. Here we make a string U containing the word "jackdaws love my big sphinx of quartz" using the string split method. We can delete the fourth element using del U3, leaving "jackdaws love my sphinx of quartz." It's also possible to remove elements by value rather than by position, using the remove method. Here we pass jackdaws to that method, giving us "love my sphinx of quartz." This is of course equivalent to using the del statement and the index method in combination. Attempting to remove an item which is not present, such as pyramid, results in a value error. Items can be inserted into lists using the insert method, which accepts the index of the new item and the new item itself. Here we create a list A containing the words "I accidentally the whole universe." We insert the word "destroyed" at index 2 using a call to the insert method, giving us "I accidentally destroyed the whole universe." We can convert this list of words back into a string by calling the string join operator on a space separator. Concatenating lists using the addition operator results in a new list without modification of the operands. whereas the augmented assignment operator plus equals modifies the assignee in place. This can also be achieved using the extend list method. All of these techniques work with any iterable series, not just lists, on the right-hand side. Before we move on from lists, let's look at two operations which rearrange the elements in place, reversing and sorting. A list can be reversed in place simply by calling its reverse method. Similarly, a list can be sorted in place using the sort method. The sort method accepts two optional arguments, key and reverse. The latter is self-explanatory, and when set to true, gives a descending sort. The key parameter is more interesting. It accepts any callable object, which is then used to extract a key from each item. The items will then be sorted according to the relative ordering of these keys. There are several types of callable object in Python, although the only one we have encountered so far is the humble function. For example, the built-in len function is a callable object, which is used to determine the length of a collection, such as a string. Consider the following list of words. Not perplexing do handwriting family where I illegibly know doctors. By passing a reference to the len function as the key argument to the sort method of the h list, we can order these words in order of length. Again, we can join the list of words back together with a call to the join operator on a space separator, giving the almost sentence, I do not know where family doctors illegibly perplexing handwriting. Sometimes an in situ sort or reversal is not what is required. For example, it may cause a function argument to be modified, giving the function confusing side effects which it would not otherwise have. For out-of-place equivalents of the reverse and sort list methods, you can use the reversed and sorted built-in functions, which return a reverse iterator and a new sorted list respectively. Here we use sorted to sort a list of numbers x, which returns a new list y. Notice that the original list x is unmodified. Here we use reversed to reverse a list of numbers p. Notice how we need to use the list constructor to evaluate the result of reversed. This is because reversed returns an iterator, a topic we'll cover in much more detail later. These two functions have the advantage that they'll work on any finite length iterable source object. We've learned a lot about lists in this section, together with some more general techniques such as slicing that can be used with other sequences including tuples and strings. Let's move on and look at the next collection type. We'll now return to dictionaries, which lie at the heart of many Python programs, including the Python interpreter itself. We briefly looked at literal dictionaries previously, seeing how they are delimited with curly braces and contain comma-separated key-value pairs, with each pair tied together by a colon. The values are accessible via the keys. The keys must be unique within any single dictionary, although it's fine to have duplicate values, so long as they're associated with different keys. Internally, the dictionary maintains pairs of references to the key objects and the value objects. The key objects must be immutable, so strings, numbers, and tuples are fine, but lists are not. The value objects can be mutable, and in practice often are. Our example URL map uses strings for both keys and values, which is fine. You should never rely on the order of items in the dictionary. It's essentially random, and may even vary between different runs of the same program. As for the other collections, there's also a named constructor, dict, which can convert other types to dictionaries. We can use the constructor to copy from an iterable series of key-value pairs stored in tuples, like this. Recall that the items in a dictionary are not stored in any particular order. So long as the keys are legitimate Python identifiers, it's even possible to create a dictionary directly from keyword arguments passed to dict. As with lists, dictionary copying is shallow by default, copying only the references to the key and value objects, not the objects themselves. There are two means of copying a dictionary, of which we most commonly see the second. The first technique is to use the copy method. Here we copy a dictionary of color codes. Note that we supply them in hexadecimal, but they're echoed back to us in decimal. The second means of copying is simply to pass an existing dictionary to the dict constructor. If you need to extend a dictionary with definitions from another dictionary, you can use the update method. This is called on the dictionary to be updated and passed the contents of the dictionary which is to be merged in. Here we merge in some additional color codes into our existing dictionary. If the argument to update includes keys which are already present in the target dictionary, the values associated with these keys are replaced in the target by the corresponding values from the source. As we have seen in an earlier module, dictionaries are iterable, so can be used with for loops. The dictionary yields the next key on each iteration, and we retrieve the corresponding value by lookup using the square brackets operator. Notice that the keys are returned in an arbitrary order, which is neither the order in which they were specified, nor any other meaningful sort order. If we want to iterate over only the values, we can use the values dictionary method. This returns an object which provides an iterable view onto the dictionary values without causing the values to be copied. There is no efficient or convenient way to retrieve the corresponding key from a value, so we only print the values here in this example. In the interest of symmetry, there's also a keys method which provides a view onto the keys of the dictionary, although it's not often used because default iteration of dictionaries is by key. Often though, we want to iterate over the keys and values in tandem. Each key-value pair in a dictionary is called an item, and we can get hold of an iterable view of the items using the items dictionary method. When iterated over, the items view yields each key-value pair as a tuple. By using tuple unpacking in the for statement, we can get both the key and value in one operation without the extra lookup. The membership test for dictionaries use the in and not in operators and work only on the keys. Here we create a dictionary mapping ISO currency codes to Unicode currency symbols. We use the membership testing operators to show that the New Zealand dollar is in the list of symbols, whereas the Macedonian dinar is not in the list of symbols. Here we use the del keyword to remove the fictional element unobtainium from our periodic table. The keys in a dictionary should be immutable, although the values can be modified. Here's a dictionary which maps the element symbol to a list of mass numbers for different isotopes of that element. See how we split the dictionary literal over multiple lines. That's allowed because the curly braces for the dictionary literal are open at the point of the line break. Our string keys are immutable, which is a good thing for the correct functioning of the dictionary, but there's no problem with modifying the dictionary values in the event that we discover some new isotopes. Here the augmented assignment operator is applied to the list object accessed through the H for hydrogen key. The dictionary is not being modified at all here, but the list is being extended. Of course, the dictionary itself is mutable. We know we can add new items. Here we add 3 isotopes of nitrogen. With compound data structure such as our table of isotopes, it can be helpful to have them printed out in a much more readable form. We can do this with the Python standard library pretty printing module called pprint, which contains a function called pprint. To use it, it's best to do something like from pprint import pprint as pp. If we didn't bind the pprint function to a different name, pp, the function reference would overwrite the module reference, preventing further access to the contents of the module. Arguably, it's poor design to have a module containing functions of the same name because of this issue. Anyway, by using ppm, we get a much more comprehensible display of our table of isotopes. Let's move on from dictionaries and look at a new built-in data structure we have not yet met, the set. The set data type is an unordered collection of unique elements. The collection is mutable insofar as elements can be added and removed from the set, but each element must itself be immutable, very much like the keys of a dictionary. Sets have a literal form very similar to dictionaries, again delimited by curly braces, but each item is a single object rather than a pair joined by a colon. Note that the set is unordered and of course has type set. Recall that empty curly braces create an empty dictionary, so to create an empty set we must resort to the set constructor, with no arguments. This is the form that Python echoes back to us too. The set constructor can create a set from any iterable series, such as a list. Duplicates are discarded. In fact, a common use of sets is to efficiently remove duplicate items from a series of objects. Here we remove duplicates from the list 1421799, resulting in the set 12497. Naturally, sets are iterable, although the order is arbitrary. Membership is a fundamental operation for sets, and as with the other collection types, is performed using the in and not in operators. To add a single element to the set, simply use the add method. Adding an element that already exists has no effect, and neither does it produce an error. Multiple elements can be added in one go from any iterable series, including another set, using the update method. Two methods are provided for removing elements from sets. The first, remove, requires that the element to be removed is present in the set, otherwise a key error is given. The second method, discard, is less fussy and simply has no effect if the item is not a member of the set. As with the other built-in collections, set sports a copy method, which performs a shallow copy of the set, copying references but not the objects they refer to. As we have already shown, the set constructor may also be used. Perhaps the most useful aspect of the set type is the group of powerful set algebra operations which are provided. These allow us to easily compute set unions, set differences, and set intersections, and to evaluate whether two sets have subset, superset, or disjoint relations. To demonstrate these methods, we'll construct some sets of people according to various phenotypes. Olivia, Harry, Lily, Jack, and Amelia have blue eyes. Harry, Jack, Amelia, Mia, and Joshua have blonde hair. Only Harry and Amelia can smell hydrogen cyanide. Harry, Lily, Amelia, and Lola can taste phenyl thiocarbamide, or PTC. Mia, Joshua, Lily, and Olivia have O-type blood. Amelia and Jack have B-type blood. Harry has A-type blood. And Joshua and Lola have AB-type blood. To find all the people with blonde hair, blue eyes, or both, we can use the union method, which collects together all of the elements which are in either or both sets. We can demonstrate that union is a commutative operation, that is, we can swap the order of the operands, using the value equality operator to check for equivalence of the resulting sets. To find all the people with blonde hair and blue eyes, we can use the set intersection method, which collects together only the elements which are present in both sets. This is also commutative. To identify the people with blonde hair who don't have blue eyes, we can use the set difference method. This finds all of the elements which are in the first set which are not in the second set. This is non-commutative because the people with blonde hair who don't have blue eyes are not the same as the people who have blue eyes but don't have blonde hair. However, if you want to determine which people have exclusively blonde hair or blue eyes but not both, we can use the symmetric difference method. This collects all the elements which are in the first set or the second set but not both. As you can tell from the name, symmetric difference is indeed commutative. In addition, 3 predicate methods are provided which tell us about the relationships between sets. We can check whether one set is the subset of another set using the isSubset method. For example, to check whether all of the people who can smell hydrogen cyanide also have blonde hair, use smellhcn.isSubset blonde hair. This checks that all of the elements of the first set are also present in the second set. To test whether all of the people who can taste phenyl thiocarbamide can also taste hydrogen cyanide, use the isSuperset method. To test that two sets have no members in common, use the isDisjoint method. For example, your blood type is either A or O, never both. We encourage you to experiment with these methods and become comfortable using them. They can make for some very elegant solutions. That completes our tour of the collection types in Python. But we're not quite finished. Let's complete this module by looking at the protocols which unite these collections and allow them to be used in standard ways. In Python, a protocol is a set of operations or methods that a type must support if it is to implement that protocol. Protocols needn't be defined in the source code as separate interfaces or base classes as they would in a nominally typed language such as C# or Java. It's sufficient to simply have an object provide functioning implementations of those operations. We can organize the different collections we've encountered in Python according to which protocols they support. Support for a protocol demands specific behavior from a type. As you can see from this table, most of the collection types we've looked at support the container, sized, and iterable protocols. Many of them are also sequences. The mutable protocols are each represented by only one type we have encountered. The container protocol requires that membership testing using the in and not in operators be supported. The size protocol requires that the number of elements in a collection can be determined by passing the collection to the built-in len function. Iteration is such an important concept we're devoting a whole module to it later in this course. In short though, iterables provide a means of yielding elements one by one as they're requested. One important property of iterables is that they can be used with for loops. The sequence protocol requires that items can be retrieved using square brackets with an integer index, that items can be searched for with the index method, that items can be counted with the count method, and that a reversed copy of the sequence can be produced with the reversed built-in function. We won't cover the mutable sequence, mutable mapping, and mutable set protocols here, since we have only covered one representative of each protocol, so the generality afforded by the protocol concept doesn't gain us much at this juncture.